know that maybe we are running a bit out of schedule, but that doesn't matter because basically we prefer for us, let's say, to cover most issues. I mean, we have all these experts with us today, so we prefer, let's just make use of them. And if there are other issues like, okay, I'm not saying that the consultation is not important. We do have 2 hours for that. So
yeah,
maybe
we have time for that.
Yes, maybe we do have time for that. So I prefer for us, let's say, to focus a bit more on using these guys that are here and their expertise. I didn't mention that, but Carlos Martinez and Cristiano Flarty and Mark Pastors, who will be presenting later, all of them are attending what we call the Internet Engineering Task Force events. At those particular meetings, you have all these experts coming together, and they are the guys who are, let's say, drafting all these internet-related standards. So we have some key people with us today. So let's just, and I guess based on what he has been doing and explaining, I think you agree with me that he's an expert. So let's just make use of them. Okay? Thanks.
Thank you, Sean. A little ad for the AETF. You have an upcoming AETF which is kind of close. It's in Atlanta in the 2nd week of November. And I guess you probably can get there fairly cheap from here. So if you are interested in these kind of things, I would highly recommend you guys to attend at least a couple of days of the AETF. I could be glad to help you identify which working groups if you're interested in certain topics, but also Christian, Mark, and Shannon can help you with that. Okay, if you look at the agenda, I was supposed to start talking about routing now. I will make a small detour there because I want to give 5 minutes to talk about auto-configuration mechanisms. Why I think this is important is because if you're going to try this in your lab, in your house, you will need auto-configuration, and it's an important topic actually because it works kind of different from what we are used to in IPv4. What do we use for host auto-configuration in IPv4? DHCP, right? Everybody does DHCP. What do we use it for? We use it for auto-configuring addresses, host addresses. We use it to get DNS server addresses. We use it to get also router addresses, default gateways, right? All the basic things you need to actually connect to the internet, you get through your DHCP server. Now, the key word there is server. You need to have a server, which is, it can be a machine, it can be a feature of a router, but you need something that keeps track of what addresses have been leased or are in use in the network, okay? So you have something that keeps state in the network. Now, it's not that bad because actually it isn't a box that is doing traffic things like an ad box, but in some scenarios, keeping state, it's a lot of work. So this is when where the IPv6 protocol discussion started. Someone said, what about if we created a stateless auto-configuration mechanism? So in IPv6, we came to this point where we have basically 2 ways of auto-configuring hosts. One stateless and one stateful, okay? Stateful is basically the DHCP, which is called DHCP version 6. It has had kind of a troubled history because it wasn't, there was a lot of discussion at some points and people didn't agree with different topics until very recently. And for a long time, IPv6 auto-configuration was mainly done in a stateless way. But you can do reasonable stateful auto-configuration right now. So, stateless auto-configuration. So, we need to have a way of auto-configuring addresses. This is the first point that we are going to address, is how to auto-configure addresses. So, don't worry about the last part. I'm going to talk about that in a few minutes. The idea is with the stateless auto configuration, or SLAC, as it's sometimes called, you can get your IPv6 prefix, not your address, but your prefix. What does it mean? Is that, remember how we split the address between lower 64 bits and higher 64 bits? What the server or the router is going to provide you is only with the high part of the address. You are going to create your own lower part, applying a similar algorithm to the ones that we mentioned with the link local addresses. Basically using a seed, which is the MAC address, and applying some algorithm to it. The algorithm can be very stupid, like just putting the MAC address there, or it can be something more sophisticated that creates something that is not recognizable, or it's different from the MAC address in some way. We are going to get from stateless also the router, the default gateway, and some other parameters like the link local MTU and the hop limit. Okay, these advertisements, these prefix advertisements, will also have validity lifetime. Okay, if they will expire at some point, you will need to recheck the network in order to see if your prefix has changed. So DNS server addresses were in the past not supplied over Slack. The thing is, this works now. Okay, this slide deck is kind of old in that sense. This works now. Recent operating system, this basically works. Okay. In stateless, you will, as I mentioned, build your global address using the link prefix, which you get from the router, from the local system that advertises the prefix, plus something you calculate, in this case using this algorithm, based on the MAC address. The hosts will listen from certain messages, which we call the array messages. In any discussion on IPv6, you will listen to array a lot. This array comes from router advertisement. And basically, these messages sent to the link will provide the host with the information they need to auto-configure themselves. As I mentioned, the IPv6 addresses will usually be based on the MAC address, although, and this has been a concern raised in the past, since the MAC address is unique, kind of unique per system, privacy concerns about this. Okay. Remember that I didn't bring up the privacy concerns with the link local addresses because the link local addresses are linked local, so no one else in the world should see them. But since these are global addresses, you could worry about being tracked through your MAC address. The thing is, it was a reasonable concern, and thing called privacy extensions was designed and created to address this, this concern. Privacy extensions will actually create a unique address using the MAC address as a seed, applying a crypto algorithm, whatever, and basically will also rotate the address so you don't have a unique address all the time, which helps in terms of privacy. This doesn't mean that they will protect you in a perfect way, right? There are many other ways of tracking users, like Christine showed us yesterday, cookies, whatever. It's even, you know, in a CGN future, I actually willing to bet that cookie tracking will be much more worrisome than any tracking you can do with IP addresses. But it's okay that you use IPv6 privacy addresses. For example, Windows will use privacy addresses by default. Linux won't. I'm not sure about the latest kernels. I don't think you need to enable them, but it also has the concept of privacy addresses. Some people would expect this privacy address to be completely untrackable. It's okay, it doesn't work that way anyway. The idea is that it will provide you to a comparable level of privacy that you have today with IPv4. It's not perfect. The thing is, it tries not to be worse, and perhaps better in some ways. I'm not a fan of Windows usually, but I can tell you that the IPv6 implementation, stack IPv6 implementation, which is probably the best and most complete one. It even had support for stateless DNS configuration before the Mac, which is something. Okay, how does it work? When the machines boot, they will get a link local address, and they will run a step which is the DAD, or duplicate address detection. Remember that I mentioned that this thing with the MAC address has a reasonable expectation of being unique, but it doesn't have a guarantee of being unique. So you need to do something about that. There is a step called the duplicate address detection. Basically sends some proofs into the network to see if the address is already used, and it will reseed the algorithm in a way that allows it to generate a new one and try again. It usually doesn't happen that much. And once it has its addresses, it will basically do this, send a router solicitation message. And the router, come on, okay, should answer with the RA message. Okay? Contains the address of the router, and you can see what's going on here, okay? It will take the prefix, okay, the higher 64 bits, and use these lower 64 bits and build the global address, okay? It's a very simple process, actually. This is a few exchanges of messages, and it happens very, very quickly. You hardly notice that. When you're working in an IPv6 network, you hardly notice that. Then you set the default router. Usually you will see the link local address used as the default gateway. Okay. I'm not sure if it should always be the link local, and I'm pretty sure I've seen different things, but usually you will see the link local address used as the default router. Okay, this is basically stateless auto configuration. It's a very simple mechanism. You can see that no system in the network is keeping track of which addresses are being used. The duty of detecting duplicate addresses is left on the hosts. The hosts are responsible for ensuring that the addresses are unique within this segment. Okay? This usually is someone's company or someone's house, right? It shouldn't be a problem with the operators, so don't concern yourself with that. For you operators, you will usually configure routers statically, right? Unless you have servers. Or, sorry, servers you will probably configure statically as well. For workstation network, you will have something like this. Now, the fact that no one is keeping track of which addresses are in use actually presents a challenge in some deployments, in the sense that what do you do when you have, for example, a machine that is infected with some kind of malware? What do we do now in IPv4? We take the address, right? And how do we find that machine? We usually go to the DHCP log, right? We get the MAC address for that. And then you go to the switches, right? And search for the port on which that MAC address is connected to. Okay? And then you just go and hit the guy in the head with something, okay? The thing, you don't have that here, okay? You could, if you are not using privacy addresses, you could try to infer the MAC address from the address that is generating the bad traffic, but it's kind of hard, right? So it's, you probably won't use stateless auto configuration in an enterprise network. But the good thing is that you have also the DHCP version 6, okay? Which works basically the same with a few quirks here and there as the DHCP version 4. The big problem with the DHCP version 6 was there was little support from operating systems until very recently, like Windows 7 and OS X Lion, I think. I'm not sure about Linux though. I think you can get the HTTP version 6 client, but you have to install it. It's not like in the kernel, it's like a user mode application. But I think it basically works also. We've been trying it in LACNIC we don't have this huge part of machine. We have like 30 or 40 machines, user machines, and basically works. This will provide you with the same logging capabilities as the HTTP version 4 server, and okay, the concern about logging should be recently addressed using the HTTP version 6. If I have to recommend you something, you should do a little trial first, because as I mentioned, until recently, support on operating system for the HTTP version 6 was a little bit immature. I won't go into this because the idea is basically the same. It works just like the HTTP. I mean, the transport is different. It uses multicast instead of broadcast. Remember that the HTTP in version 4 was broadcast. It uses multicast. It uses the link local addresses to transport the messages, but the concept is basically the same. Okay, so routing protocols. Now, as I mentioned, the auto configuration was important if you're a home user. Now, this is the part that is important if you're an ISP or a network operator, right? Routing protocols. If you're an ISP, this is what you do for a living, right? You route packets from point A to point B. So we, and I say we because I used to do this for a living too, we live and die by routing protocols. So the first one I'm going to talk about, you will see that this is very similar to before. And if it looks like the same, it's because it's mostly the same, and I will point you to some differences, but in the end it's basically the same. The first one I'm going to talk about is not exactly a routing protocol, but it's something which is sometimes important if you have a server farm, for example, which is VRRP. VRRP is a virtual redundancy routing protocol, which provides you with a way of providing servers and hosts with transparent default gateway redundancy. Okay. Why this is important? Because usually servers and hosts do not speak routing protocols. If the default gateway goes down, their network connectivity goes down. So, very common concern is how do you provide to a kind of dumb server or host with redundancy at the default gateway level? So the answer was, okay, you put two routers, okay? But then how does the host knows which one to use? And then came a Cisco solution a while ago, like 15 years ago, which was called, if I remember correctly, HSRP or something like that. Which basically created a little keep alive protocol between two routers and created the concept of an active and a backup default gateway. And the keep alive protocol allowed it to actually the routers detect if one of them was down. Each one will have a virtual address, each one will have a physical address, and both of them will coordinate between themselves to provide a virtual IP address for the servers to use as the default gateway. Okay? This worked out very well, actually. And it was such a good idea that at some point the IETF decided to do something about that, and it standardized VRRP. March 2010, VRRP version 3 actually added support for V6 on this redundancy protocol. Again, we use multicast for the signaling. Multicast is really important in V6, you will see. This has some interesting implications. If you're filtering multicast at the layer 2 level, which some people do, for security reasons, valid security reasons, you need to revise a little bit that policy because you will break some IPv6 functionality that you need that rely on multicast to work. Okay. There were for example, some older Cisco access points that they filtered multicast by default, which was kind of tricky. In fact, I spent a whole day one day in a workshop in Honduras trying to see why nothing worked. And it was like an old iOS version that was filtering multicast by default. Christian remembers that because he was there too. Okay. Now to the routing protocols themselves. RIP. Everybody remembers RIP here? RIP version 1, RIP version 2. Old stuff, old school stuff. So why I'm talking about RIP? Okay, RIP, remember it was the old distance vector protocol. Remember the routing protocols can be classified in two groups, like 3 groups actually, but 2 main ones. Distance vector and link state routing protocols. Distance vector work on a very simple assumption, that is, if I know how to reach my neighbors, which is something I obviously know, because I know who my neighbors are the routers that are directly connected to me. If I tell my neighbors who my neighbors in turn are, my neighbors will know how to reach mine, because they are going to basically build actually a distance vector. This is what's called a distance vector protocol that says, okay, in order to reach C, I need to go through B. And they will compute the distance adding 1 to the hop count. Okay, this is a very old algorithm, very well understood algorithm. It comes from, I would say, 50 years ago or something like that. It started with a completely different application than routing. It has a lot of problems, like this count to infinity issue. If you remember your university IPv4 stuff, you will remember things like split horizon and count to infinity and the maximum 15 hop limit that it's needed to actually mitigate the count to infinity issue. So it's basically why OSPF was invented, because RIP had so many limitations that made it impossible to use it in a large deployment. So why did we create a new RIP for v6? The thing is, when the IPv6 standardization process began and you needed to run it on first few routers, actually RIP is very easy to implement. So there was a reasonable expectation that if you needed something for a quick fix and for a few testing, you would implement RIP. Okay. Then fast forward like 15 years, and then since we expect people to run VLANs in their homes at some point, so everybody agrees that technology is going in a way that since you are going to have so many devices connected in your house, like your fridge, your washing machine, whatever, and you don't want them to be in the same security zone, for example, you will need VLANs, some way to segment your network. So right now the ATF is working on a document that says which are the the home router requirements. And one of the requirements is some form of routing protocol. And since it's a very little thing, RIP actually makes sense in that deployment. So RIP and G may make some form of comeback in the future or not. But this is why we keep it in the slides, because you perhaps will see it in the future. Okay, then to the big, I'm moving to the two big guys, ISIS and OSPF. So, I'm sure everybody knows about OSPF. It's the Open Shortest Path First protocol. It's a link state protocol that works very well. It's very well implemented. All major platforms support it. But it had one major drawback. If we go back to 15 years ago, it didn't support multiple other families. Hence, it didn't support IPv6. So, while the ATF was concerned in extending OSPF in a way that it supported multiple other families, what came to be OSPF version 3 later on, someone had this idea. They decided to go to the land of the undead, the OSI stack, the old 7-layer networking stack, And they discovered that there was a routing protocol there that was actually a good one. ISIS, which is the intermediate system to intermediate system protocol, is also a link state protocol. It employs some of the same concepts as OSPF, but it's implemented in a way that it can be extended very easily to support multiple address families. In fact, someone had already done that. I think it was Cisco, the first one. They had extended, ISIS was obviously designed to transport OSI protocols, like CNLS. Cisco had already extended it to support IPv4. So it was very easy also to extend it to support IPv6. And people found that it actually works very well. So why? And there was an additional issue that when OSPF version 3 first came out, even it was designed in a way that would be extended easily, it only supported IPv4 also. Okay, sorry, it only supported IPv6. So if you wanted to run OSPF in your network, you ended up with 2 routing protocol instances in your routers, one for IPv4, one for IPv6. As you perhaps remember, OSPF relies on something because it's called the Dijkstra algorithm, which is a computationally complex algorithm, and you don't want to run it twice. Perhaps now with current technology it's not such of a concern, but at some point it was. So ISIS offered people the way forward with running only one instance of the Dijkstra algorithm and running only one protocol. Okay, even if it comes from the land of the things we don't like so much, they actually do some good work. The key for extensibility in ISIS is this thing. The messaging in ISIS is defined in a way that is generic. It uses which is called a tag length value, which is basically a data structure that you can extend. And the transport of the protocol is agnostic to that. And you can transport new ones. You just create a new TLV, or in this case, 2 TLVs, to actually transport IPv6 reachability information. And there you go. Actually, this came to be earlier than OSPF version 3 because it wasn't a new protocol. It was just a small extension to something that already existed. The IETF actually realized that it was a good idea and actually reissued the ATU standard in a RFC, a couple of RFCs. So this is now basically supported by every major routing provider. And I tried it, although I prefer OSPF for my deployments. I have to tell you that it works very well. In my previous employer, until in Uruguay, we used ISIS for a long time, and we didn't have any major issues. Basically, if you want to use it, it's actually a good thing. OSPF version 3. OSPF version 3 works the same as OSPF version 2 conceptually. If you remember this, you will remember the backbone area, area 0. Every area areas are segments within the network, subsets of the network. Each area has to be connected to the backbone area. And inside each area, you run the shortest path first algorithm based on a set of messages that are called LSAs, that are basically flooded into the network. What do we mean by flooding? When a router generates one of those messages, the other router will just broadcast them on all of the other links. Okay? There are some mechanisms implemented on top of that, so to avoid the network basically from melting down. So after the packets go a few loops inside the network, they are dropped. But the thing is, you need to keep your areas reasonably small so this flooding doesn't affect you too much. This is what it says, the LSA flooding is bounded by area. Shortest path first is run per area as well, which keeps the graph for the Dijkstra algorithm reasonably small. And again, this works very well. This works very well, and it converges very quickly. For example, one of the concerns you always have with a routing algorithm is how fast it will provide you with a valid routing table. RIP will take sometimes times in the order of minutes to provide you with a valid routing table after a network event. OSPF can provide you with this in terms of seconds, okay? Even for large networks. ISIS as well, because they're based on the same concept. OSPF used to be an IPv6 only protocol, so again, you don't need to concern about that now. And we have tried this at our network LACNIC we use Juniper equipment right now. OSPF version 3 will happily route IPv4 and IPv6 for you. So you don't need the dual slices anymore. We found a funny bug in a Cisco implementation, in our 6 deploy line, in fact. If you enable OSPF version 3 only on an area, then it won't route IPv4. But it's due to a bug. You actually need to just enter one OSPF version 2 command, which is router OSPF something. You don't need to configure anything else. Just that line in the configuration will enable OSPF version 3 to route IPv4 as well. They promise to fix it in some future version. But even if you have that line in the configuration, it doesn't mean that you're running 2 instances of the protocol. You are still running only OSPF version 3. Okay. Again, the idea is the same. You have the areas, you have the backbone. You need to connect your areas to your backbone. And as in the old OSPF version 2, these routers here in the backbone area are the only ones that have the full reachability information and know how to reach every other router in the network. Routers in these areas will know how to reach every router in their area, but they will only have a default route outside the area through these border routers. Remember that in OSPF we have the concept of the border router, which is a router that lives in 2 areas. It's actually the gateway between the 2 areas. Okay. That is with interior routing, right? ISIS, OSPF version 3, you pick your choice, choose whatever you're most familiar with. ISIS, OSPF version 3 will work very well for you in any case. Down multi-protocol BGP. Now, when do you use BGP? Right? When you connect your autonomous system to other autonomous systems. And sometimes you run BGP inside your network. For example, if you're providing MPLS VPNs to your customers, you will probably run BGP inside your network as well. So, in fact, MPLS VPNs was the reason why BGP had already been extended to support multiple address families. So adding IPv6 to BGP was easier than with OSPF. Again, how does it work? It works in the same way. Okay, you will have your IPv6 prefixes. BGP will basically announce your table of IPv6 prefixes to your peers, and your peers will apply their BGP decision algorithm. Remember the long list of like 12 or 13 steps, 14 if we had a KI, steps in order to decide whether to use a prefix or not. Okay? It works exactly the same. There is one caveat now. I will go into that in a few minutes. Supports the same features, same functionality, and the good thing is that it's already multi-protocol. It doesn't only support IPv4, it supports IPv6, but it also supports multicast. And it also supports MPLS VPNs, which is called is BRF something. It's called the address family, the name of the address family. Okay. IPv4 and IPv6 will have or can have their own routing policies. You are not forced to apply the same routing policy to IPv4 to IPv6. You can make different transit decisions. For example, if you prefer an upstream provider for IPv4, you can prefer a different one for IPv6. Okay, that's not a problem. Okay, and this is where one caveat case to multi-protocol BGP. It has to do with how the next hop is computed. When you establish a BGP session, those of you who have configured BGP will remember this. The next hop of the routes is computed based on the peering addresses that are used for the BGP session itself. So it's very good if you're using an IPv4 BGP session for transporting IPv4 prefixes, right? But if you're using an IPv4 BGP session for transporting IPv6 prefixes, which actually works and you can do that, then the next hop calculation has something of a problem, okay? How do you fix that? Basically, you explicitly tell per session which next hop address to use, right? In Cisco, for example, you would say next hop something, okay? It happens exactly the same if you use an IPv6 session to transport IPv4 prefixes, and you fix it in the same way. However, some people prefer to actually use an IPv4 session, an IPv6 session for before and IPv6 prefixes on the same link, even if it's on the same link. Actually, we have it configured that way with our upstreams in our office. We have configured that way. We have an IPv4 session for IPv4, an IPv6 session for IPv6. But you can do it the other way as well. It's not a problem, actually. Okay. RFC, and this is basically it. If you think this was short and it was the same on IPv4, it's basically it was. I tried to point you the main differences and things you should be careful about, but this is actually probably the aspects of IPv6 that are more mature and are best solved and best implemented in routers have to do with core routing. Like BGP, OSPF, ISIS are the ones who are the most mature technologies in IPv6. They were the first who came to be, and they are the ones who have been the most widely deployed in the networks. So basically, the problems related to them are best understood. So thank you so much. If you have any questions now or later, please let me know. And I really appreciate Shannon's patience with the time and with me. Thank you so much.